dear students, today we are going to discuss the topic on methods of measurement and detection of radioactivity with particular reference to Geiger-Müller counter and scintillation detectors. The main objectives of the topic are to throw light upon the methods of measurement and detection of radioactivity, define detectors with particular focus on Geiger-Müller counter and scintillation detector, to discuss different types of Geiger-Müller counter and scintillation detectors, and to study applications and limitations of detectors. Now, let us start with a brief introduction. Radioactivity was discovered by Henry Becquerel in 1896. The term radioactivity was actually coined by Marie Curie, who, together with her husband Perry, began investigating the phenomena recently discovered by Becquerel. The Curies extracted uranium from ore and, to their surprise, found that the leftover ore showed more activity than the pure uranium. They concluded that the ore contained other radioactive substances. This led to the discoveries of the elements polonium and radium. The activity of a radioisotope source is defined as its rate of decay. The probability that a particular nucleus will undergo radioactive decay during a fixed length of time does not depend on the age of the nucleus or how it was created. Although the exact lifetime of one particular nucleus cannot be predicted, the mean lifetime of a sample containing many nuclei of the same isotope can be predicted and measured. Now, let us start with brief introduction about measurement and detection of radioactivity. A measurement is an attempt to determine the value of a certain parameter or quantity. Anyone attempting a measurement should keep in mind the two axioms regarding the result of the measurement. Axiom first is no measurement yields a result without an error. Axiom second is the result of a measurement is almost worthless unless the error. Now, coming to the types of errors. There are many types of errors, but they are usually grouped into two broad categories, systematic and random. Now, systematic or determinate errors are those that affect all the results in the same way. Examples of systematic errors are: first, errors from badly calibrated instruments; second, personal errors, that is algebraic wrong readings, etc. Third is imperfect technique. Now, systematic errors. Systematic errors introduce uncertainties that do not obey a particular law and cannot be estimated by repeating the measurement. The experimenter should make every reasonable effort to minimize or eliminate systematic errors. Once a systematic error is identified, all results are corrected appropriately. Random or statistical errors can either decrease or increase the results of a measurement, but in a non-reproducible way. Most of the random errors cannot be eliminated. They can be reduced by either improving the experimental apparatus, improving the technique, or repeating the experiment many times. Examples of random errors are: first, errors resulting from experimental apparatus, that is, reading of instruments, electronic noise, etc. Second is errors from uncontrolled change in conditions such as voltage, temperature, or pressure. Third is probabilistic nature of the phenomena under study. The objective is to present methods that provide an estimate of the error of a certain measurement or a series of measurements and procedures that minimize the error. In every measurement, systematic and random errors should be treated separately. Now, what are detectors? The function of a detector is to produce a signal for every particle entering into it. Every detector works by using some interaction of particles with matter. Following is a list of the common detector types. First is gas-filled counters, for example, Geiger-Müller counters. Second is scintillation detectors. Third, semiconductor detectors. Fourth, spark chambers. Fifth, bubble chambers. Sixth, photographic emulsions. Seventh, thermoluminescent dosimeters. Eighth, Cherenkov counters. And ninth is self-powered neutron detectors. Now, What is Geiger-Müller counter? The Geiger counter is an instrument used for measuring ionizing radiation, used widely in such applications as radiation dosimetry, radiological protection, experimental physics, and the nuclear industry. It detects ionizing radiations such as alpha particles, beta particles, and gamma rays using the ionization effect produced in a Geiger-Müller tube. It's perhaps one of the world's best known radiation detection instruments. The original detection principle was discovered in 1908 at the Cavendish laboratory, but it was not until the development of the tube in 1928 that the counter became a practical instrument. Since then, it has been very popular due to its robust sensing element and relatively low cost. Now, what is the principle of its operation? A Geiger counter consists of a tube, the sensing element which detects the radiation, and the processing electronics which displays the result. The tube is filled with an inert gas such as helium, neon, or argon at low pressure, to which a high voltage is applied. The tube briefly conducts electrical charge when a particle or photon of incident radiation makes the gas conductive by ionization. The ionization is considerably amplified within the tube by the Townsend discharge effect to produce an easily measured detection pulse which is fed to the processing and display electronics. This large pulse from the tube makes the GM counter relatively cheap to manufacture, as the subsequent electronics is greatly simplified. The electronics also generates the high voltage, typically 400 to 600 volts, that has to be applied to the tube to enable its operation. There is usually an option to produce audible clicks representing the number of ionization events detected. This is the distinctive sound normally associated with handheld or portable Geiger counters. Now, next is particle detection. First is alpha particles. For alpha particles and low energy beta particles, the end window type of GM tube has to be used, as these particles have a limited range even in free air and are easily stopped by a solid material. Alpha particles have the shortest range, and to detect these, the window should ideally be within 10 mm of the radiation source due to alpha particle attenuation in free air. However, the GM tube produces a pulse output which is of the same magnitude for all detected radiation, so a Geiger counter with an end window tube cannot distinguish between alpha and beta particles, but with the detector in close contact with the radiation source, the two types are both detected and are indistinguishable. The pancake detector is a variant of the end window probe, but designed with a large detection area to make checking quicker. However, the pressure of the atmosphere against the low pressure of the fill gas limits the window size due to the limited strength of the window membrane. Second is beta particles. Some beta particles can also be detected by a thin-walled windowless GM tube, which has no end window but allows high-energy beta particles to pass through the tube walls. Although the tube walls have a greater stopping power than a thin end window, they still allow these more energetic particles to reach the fill gas. End window GM detectors are still used as a general purpose portable radioactive contamination measurement and detection instrument. Owing to their relatively low cost, robustness, and their relatively high detection efficiency, particularly with high energy beta particles. Third is gamma and X-ray detection. Geiger counters are widely used to detect gamma radiation, and for this the windowless tube is used. However, efficiency is generally low due to the poor interaction of gamma rays compared with alpha and beta particles. For high energy gamma rays, it largely relies on interaction of the photon radiation within the tube wall material, usually 1 to 2 mm of chrome steel on a thin wall tube, to produce electrons within the wall which can enter and ionize the fill gas. Low energy photon radiations such as low energy X-rays or gamma rays interact better with the fill gas. Consequently, a typical design for low energy photon detection for these is a long tube with a thin wall or with an end window. The tube has a larger gas volume than a steel wall tube to give an increased chance of particle interaction. Fourth is neutron detection. A variation of the Geiger tube is used to measure neutrons, where the gas used is boron trifluoride or helium-3, and a plastic moderator is used to slow the neutrons. This creates an alpha particle inside the detector, and thus neutrons can be counted. Now, coming to the advantages of Geiger-Müller counter. First, GM detectors are fairly reliable and rugged instruments used for field use applications. Second is, they are easy to use and come in a wide variety of shapes and sizes. Third is, they are portable and lightweight and are relatively inexpensive. Fourth is, GM counters respond quickly to radiation and are sensitive to relatively low levels of radiation. Fifth is, GM counters can detect a wide variety of radiations, including alpha, beta, X-ray and gamma rays. Sixth is, they are frequently used to survey for contamination on equipment and can be modified to make exposure rate measurements. Now, coming to the limitations of Geiger-Müller counter. There are two main limitations of the Geiger counter. First is, the output pulse from a tube is always the same magnitude regardless of the energy of the incident radiation. The tube cannot differentiate between radiation types. Second is, a further limitation is the inability to measure high radiation rates due to the dead time of the tube. Now, coming to the scintillators. Scintillators are materials, solids, liquids or gases that produce sparks or scintillations of light when ionizing radiation passes through them. The first solid material to be used as a particle detector was a scintillator. It was used by Rutherford in 1910 in his alpha scattering experiments. The amount of light produced in the scintillator is very small. It must be amplified before it can be recorded as a pulse or in any other way. The amplification or multiplication of the scintillator's light is achieved with a device known as photomultiplier tube. It accepts a small amount of light, amplifies it many times, and delivers a strong pulse at its output. The different types of scintillators are divided into three groups. First is inorganic scintillators, second is organic scintillators, and third is gaseous scintillators. Now, first, inorganic or crystal scintillators. Most of the inorganic scintillators are crystals of the alkali metals, in particular alkali iodides, that contain a small concentration of an impurity. Although the activator has a relatively small concentration, it is the agent that is responsible for the luminescence of the crystal. Now, the mechanism of the scintillation process. The luminescence of inorganic scintillators can be understood in terms of the allowed and forbidden energy bands of a crystal. In a crystal, the allowed energy states widen into bands. In the ground state of the crystal, the uppermost allowed band that contains electrons is completely filled. This is called the valence band. The next allowed band is empty and is called the conduction band. An electron may obtain enough energy from incident radiation to move from the valence to the conduction band. Once the electron is free to move anywhere in the lattice, the removed electron leaves behind a hole. The electron-hole pair thus formed is called an exton. In terms of energy states, the exton corresponds to elevation of the electron to a state higher than the valence but lower than the conduction band. Second is organic scintillators. The materials that are efficient organic scintillators belong to the class of aromatic compounds. Organic scintillators are formed by combining appropriate compounds. They are classified as unitary, binary, ternary, and so on, depending on the number of compounds in the mixture. The substance with the highest concentration is called the solvent. The others are called solutes. A binary scintillator consists of a solvent and a solute, while a ternary scintillator is made of a solvent, a primary solute and a secondary solute. Now, its mechanism of scintillation process. The production of light in organic scintillators is the result of molecular transitions. The ground state of the molecule is at a point A0, which coincides with the minimum potential energy. Ionizing radiation passing through the scintillator may give energy to the molecule and raise it to an excited state, that is the transition A0 to A1 may occur. The position A1 is not the point of minimum energy. The molecule will release energy through lattice vibrations and move to point B1. The point B1 is still an excited state, and in some cases the molecule will undergo the transition B1 to B0 accompanied by the emission of the photon with energy equal to EB1 minus EB0. However, it should be noted that the energy of the emitted photon is less than the energy caused by the excitation. Now, next is organic crystal scintillators. No activator is needed to enhance the luminescence of organic crystals. In fact, any impurities are undesirable because their presence reduces the light output, and for this reason the material used to make the crystal is purified. Next is organic liquid scintillators. The organic liquid scintillators consist of a mixture of a solvent with one or more solutes. In a binary scintillator, the incident radiation deposits almost all of its energy in the solvent, but the luminescence is due almost entirely to the solute. If a second solute is added, it acts as a wavelength shifter, that is, it increases the wavelength of the light emitted by the first solute so that the emitted radiation is better matched with the characteristics of the cathode or photomultiplier tube. Liquid scintillators are very useful for measurements where a detector with large volume is needed to increase efficiency. The liquid scintillators are well suited for such measurements because they can be obtained and used in large quantities and can form a detector of desirable size and shape by utilizing a proper container. Now, lastly coming to gaseous scintillators. Gaseous scintillators are mixtures of noble gases. The scintillations are produced as a result of atomic transitions. Since the light emitted by noble gases belongs to the ultraviolet region, other gases such as nitrogen are added to the main gas to act as wavelength shifters. Thin layers of fluorescent materials used for coating the inner walls of the gas container achieve the same effect. With this, we come to the end of today's lecture.